Hello everyone, we are Senior Design Team 6 with the Wildlife Imager. The goal of our project was to improve, develop, and manufacture a device to help natural resource management researchers obtain accurate volume measurements of American pine marten dens. The current approach used by the GVSU NRM department involved researchers physically climbing trees to access wildlife dens, relying on flashlights to visually inspect the narrow openings. This method posed a significant safety risk to the researchers and increased the likelihood of disturbing the animals. Additionally, it did not provide any quantitative data for analysis. In previous years, another senior design team developed a device. Their prototype was semi-functional, but it had a few issues, including it wasn't drop resistant, had inconsistent sensor readings, and some other problems. But overall, it was not ready for reliable field deployment. Starting with mechanical design, some key specifications the team had to follow included that the device had to be easily assembled, needed to fit into a 10 centimeter in diameter hole, needs to reach a den 20 feet high, be drop resistant, be water and dust resistant, and then the pole and device must weigh less than or equal to 13 pounds. The device enclosure is where all the time-of-flight sensors and electronic components are housed. The enclosure has a 7 centimeter diameter sized to fit through 10 centimeter openings. A 4-bolt compression system with an O-ring seal was selected for reliable sealing, easy access, and environmental protection. The enclosure is 3D printed using a tough 2000 resin to ensure it can survive a 6-foot drop into compact sand. Shown are all the software design key specifications. The Wildlife Imager software consists of an Android app and embedded firmware, communicating via a BLE GATT profile. The app is built in Colton with a MVVM architecture, allowing users to start captures, view sensor data, and monitor device status. The results are shown in a point cloud, mesh view, and overall calculated volume. The embedded firmware structured with free RTOS and centralized finite state machine manages sensor control, data processing, and communication. It coordinates 14 time-of-flight sensors across a dual I2C bus, processing point cloud data and reports data back to the app. Next are the key specifications for the electrical design. These included accurately measuring volumes within plus or minus 10%, have a 30-minute minimum battery life, be able to store data to be reviewed at a later time, and have a tablet to display 3D volume measurements and communicate with the system to take measurements. To estimate object volume, each time-of-flight sensor generates a 64.3D point cloud using its 8x8 array and 60° by 60° FOV. The distance data is then converted into XYZ coordinates. These individual clouds are fused together by transforming each sensor's data into a common origin using 3D rotation matrices and position of offsets, forming a full point cloud centered on the probe. Sensors are pre-calibrated to account for cover glass with a user-friendly calibration box provided for recalibration. Tolerance studies confirmed that both positional and rotational sensor variations result in minimum volume error. A rigid PCB integrates all key electronics, including power management, microcontroller, antenna, SD card, flex connectors, and debug interfaces. A 6-layer design ensures signal integrity. Power is supplied by a LiPo battery regulated to 3.3 volts and 1.8 volts, with a USB-C charging and Hall effect sensor for activation. The microcontroller manages Bluetooth, SD storage, and sensor control, with debug access via mediator antennas to ensure reliable wireless communication. The SD card connects via SPI, and flex PCB connectors feature voltage level shifting and control pins for sensor operation. 2 flex PCBs hold 7 time-of-flight sensors and connects to the rigid PCB via ZIF interface. The flex PCBs are 2-layer boards with signal traces on one layer and routing to sensors via the second layer. Hatched ground planes provide signal return paths, and teardrop vias prevent copper cracking in the alignment behind the cover glass, with additional stiffening at the connector. Each sensor connects to a shared I2C and reset line with separate communication enable lines. Here we can see various uses of our device. First is in a high tree. Next case is in a low stump. No. Thanks for watching.